Okay, so this is what I'm going to talk about. I'm going to talk about three basic problems, well, maybe four. I'll say a little bit about what we've understood about the origin of chorus and hiss. I want to talk a little bit more about a different process than we studied in the 70s, and that is not only will the waves cause pitch angle scattering and consequent loss to the atmosphere, but they'll also cause stochastic acceleration, and we've been able to quantify this quite accurately. I also want to talk about some observations made on the Van Allen probes that show that the very energetic super relativistic electrons remain for a long period of time once you inject them into the plasmasphere. And we can model this quite accurately. And finally, I'll talk a little bit about diffuse auroral precipitation. In fact, I'm going to actually start on talking about that. So what are chorus waves? They're very discrete, highly nonlinear emissions with various time scales. They can be seen with discrete rising elements, but they also occur in bursts which have periodicities of 5 or 10 seconds. And inside each of these bursts, there can be many, many chorus elements. We think they're generated, and we're pretty sure they're generated, following the injection of electrons into the night side magnetosphere, inner magnetosphere from the plasma sheet. The particles, when they're injected, develop anisotropy, they become unstable, and they make the chorus primarily around the dawn side. Now, once the waves are generated, they can be generated by what we call a Doppler-shifted cyclotron resonance, in which the waves are moving in one direction, the electrons are moving in the other. And during the process of the interaction, there's an energy and momentum exchange between the waves and the particles. So we've looked at the way in which these interactions work. And if you're, for instance, concentrated on the chorus band, which typically have frequencies around a few tenths of the electron gyro frequency, this is the resonant diagram in momentum space, perpendicular and parallel momentum. These two black lines are the resonant ellipses, and you can have interactions anywhere between these two lines. If you interact near the loss cone, you can also define on this diagram the direction in which the particles, the direction where they'll diffuse. At very low energies, there's a lot of momentum diffusion. And as the particles diffuse, they tend to move towards the loss cone because that's where there's a deficit of phase space density. And as they do so, they lose energy, and that energy goes to the waves. But the same waves at the same location also interact with very high energy electrons at very large pitch angle, near 90 degrees. And because there's usually a gradient in phase space density which falls off very rapidly with energy, the diffusion tends to go in the other direction. And these particles can be accelerated by the waves. So what we think is that this process is going on all the time. And following the injection, and this is the schematic picture of where these waves are distributed in the magnetosphere, we can have both the particles being lost and being accelerated in the radiation belts. So the first thing I want to talk about is the diffuse aurora. We all know about the discrete aurora. This is what you see with the naked eye when you go to places like Alaska. But embedded within that, and you can still see it, but it's relatively dim, there is this diffuse background, which is called the diffuse aurora, which is caused by pitch angle scattering, not by parallel electric fields. And interestingly, this diffuse background actually accounts for something like 75% of the energy input into the atmosphere. So it's a major contributor to the energy input into the atmosphere, as shown by Pat Newell. This is the energy input for weak or active times caused by the discrete aurora. And on the left-hand side is the energy input from the diffuse aurora. And you can see it's much more pronounced than the discrete aurora. It's also found primarily from midnight around to the dawn side, which is exactly where the electrons drift as they're injected into the system. So if you look at the diffuse aurora, it does change very substantially. This is a picture from Petronek, from Pixie X-ray detectors, which are measuring backscattered Bremsstrahlung X-rays. And if you go from weak conditions to strong conditions, there's a huge intensification of the auroral emission. The location where you see this maps very nicely, and it also shows the same distribution of the trapped electrons around a few keV. So we're measuring the precipitation of the plasma sheet electrons into the atmosphere. Now, there's been a large number of years that people have tried to understand what is the origin of this diffuse aurora. And we know it's not due to current sheet scattering or collisions. It has to be due to waves, because we're in a collisionless medium. There are these ECH waves, which are electrostatic emissions above the electron gyro frequency. Here's the electron gyro frequency. Or it could be either lower or upper band chorus emissions. And so if you look at the distribution of both of these emissions, not remarkably, they follow pretty much the same distribution as the trap particles, because it's the trap particles that are producing the waves. So in order to understand which is more important in the scattering process, you have to work out the diffusion rates. So we did this in a paper in Nature in 2010. And what we did is we took the distribution of waves seen on the CRESS spacecraft, and we worked out from the spectral properties, the scattering by ECH, upper band chorus, lower band chorus, and then all three. You can see that the chorus emissions by far dominate the scattering process. And so we think that and this paper pointed out that the chorus was the more important scattering agent, causing the diffuse aurora. But not only that, we could use the diffusion coefficients that we got to work out what the evolution of the pitch angle distribution. And you can see over a period of a few hours, you can go from a quasi-isotropic distribution into distributions which are highly anisotropic. And the anisotropy is simply due to the particle scattering. What's happening is, of course, the ECH waves only interact near the loss cone, and they cause a removal of particles in a very limited region of momentum space near the loss cone. The upper and the lower band chorus emissions interact with different energy electrons over a much broader region, and it's primarily the chorus waves that cause this evolution of the pitch angle distributions. And here's some actual data from Themis, taken not simultaneously, but statistically. On the night side, you tend to have quasi-isotropic distributions with a slight anisotropy at higher energies. But as you go around to the day side, as the electrons drift around, they develop these huge anisotropies that are called pancake distributions. And I think you'll agree that the distributions you get are very, very, very similar to what, what the simulations predict. We can also work out the timescales for this process to work, either for highly active times or moderately active times. You can compare the scattering rates with the strong diffusion rate. And during active conditions, you do indeed scatter the particles at the strong diffusion level, which would mean that the loss cone is essentially filled. Whereas in moderate conditions, the loss cones are partially empty. And that probably accounts for why the intensity of the diffuse auroral emissions show such changes during activity levels. So I want to turn now to the question of the momentum diffusion. I'm showing here some measurements taken over quite a long period of time from the Radiation Belt Storm Probe, which is now called the Van Allen Probe mission. It's taken by the MAGICE instrument and by the REPT instrument, and I know that Dan's going to talk about REPT a lot more in this session, so I won't concentrate too much on the data. But I want to point out that there are, especially at very, very high energies, abrupt dropouts, especially of the relativistic electron population. And these tend to be usually associated with abrupt increases in the solar wind dynamic pressure, times when the magnetopause is pushed into very low L shell. And that's an important thing to consider in the modeling. Also, in this third panel, we show the intensity of plasma waves seen by the emphasis wave instrument. And these are chorus emissions. And every time you have chorus emissions present extending all the way down into the inner magnetosphere, we see abrupt increases in the particle fluxes. So what I'm going to show you is some modeling we've done recently explaining the acceleration that was seen on October the 9th due to the presence of these very strong chorus emissions in the outer magnetosphere. So this is a blow-up of a figure shown in a recent paper we published in Nature last December that shows again these are the chorus emissions. Here you see the dynamic pressure of the solar wind increase. And then during this period, when the acceleration occurred, dynamic pressure was relatively low. BZ was highly negative, a lot of convective injection into the system. Very strong chorus waves were seen in both dips of the storm, but only acceleration occurred during the second phase, when the solar wind pressure was small. We also, at that time of the increase in fluxes at these energies, we found very pronounced peaks in phase space density. And these peaks in phase space density were seen in the inner part of the Earth's magnetosphere inside of L equals 5. So to model the potential acceleration of these particles by the waves, we have to have a global model for the waves. And you can't get that from measurements even on 2 spacecraft. You need a global model. So the way we do this is we use the POSE satellite data, which measures precipitating electrons in the 30 and above keV range. And if you take the ratio between the precipitated and trapped flux, this can give you a measure of the rate of pitch angle diffusion that causes these particles to be scattered into the atmosphere, and therefore it can give you a measure of the amplitude of the waves. We think these waves are present over a very broad region of the magnetosphere, and when we compare the data in the same sector we do have measurements on emphasis, we find a good agreement with the predicted wave amplitudes and the measured wave amplitudes on emphasis. So we use this model. We extend it by using these ratio between the POSE, precipitated, and trapped flux to extend the model globally, and we work out diffusion rates. And that's what's shown here. These are bounce and drift average diffusion rates in pitch angle, momentum, mixed terms, in different phases of the storm, and it goes all the way from 100 keV up to 10 MeV. We then plug these diffusion rates into a Fokker-Planck equation and do a 2-dimensional simulation of the evolution of both the pitch angle distribution and the energy spectrum of the waves. And this is what we get. So these are the observations of both the changes in the spectrum over this period of time at various energies and the changes in the measured pitch angle distribution. And these are our simulations, which gives, I think, a remarkable agreement with the observed data. And not only that, we can predict these sort of flat top distributions, which are a consequence of the very rapid momentum and pitch angle diffusion that occurs at these ultra-relativistic energies, but only at large pitch angle. To do this modeling, we didn't use statistical models for the density. We actually used a model that was based on the direct upper hybrid line and continuum radiation cutoff measured by emphasis, and scaled it to a statistical model of Scheele. And it gave us densities that were about a factor of 3 lower than the Scheele model itself. And this decrease in the density that we used in the simulation is important for 2 reasons. And this is why the outflow of material from the atmosphere plays a very key role in the instabilities that ensue and the scattering. First of all, when you decrease the density, you increase the resonant energies. Secondly, when you decrease the density, you increase, or rather you decrease the ratio between the plasma and the gyro frequency. And when this parameter is low, you get much more efficient momentum diffusion compared to pitch angle scattering loss. And this process of the reduction in the density is actually being modeled by Vanya Jordanova during the storm period, where she sees a very pronounced lowering of the plasma densities caused by the enhanced convection. So I think this is something we need to work on in the future. So the conditions, I think, that are responsible for causing very efficient acceleration in the outer radiation belt are, first of all, you need an inflated magnetosphere. And that minimizes any loss of the particles to the boundary. Secondly, you need very rapid convective injection of plasma sheet particles into the system. These provide the seed population that is eventually accelerated. They also provide the source that causes the waves to be generated. And finally, you need low plasma densities to get the acceleration occurring all the way up to 7 or so MeV. So this is the result I showed you earlier from our Nature paper, and these are results from a second paper that was written by Jeff Reeves, published in Science, showing the increase in the phase space density during the storm over about a 12-hour period, and you can start to see these very pronounced peaks in phase space density occurring. So I think we have a new concept for the energization of particles in the outer radiation belt. It's caused, of course, by the pronounced convective injection, the subsequent generation of the Whistler mode chorus emissions. These give rise to these peaks in phase space density if you have the convection occurring long enough, and eventually radial diffusion will cause the particles to very rapidly diffuse outwards, producing relatively flat distributions in the outer magnetosphere. They'll also diffuse inwards and cause some acceleration in the inner magnetosphere. How much longer do I have?
About 3 minutes.
3 minutes. Well, in 3 minutes, I'll try to zip through some new work that was done by, first of all, by Jacob Bortnick, in which we think we have finally understood the origin of plasmaspheric hiss. For many years, there was a lot of debate as to whether these waves were locally generated or whether they were produced by lightning activity that gets into the magnetosphere, and I had huge discussions and controversy with the Stanford group in particular on this, which Don knows well about. But we finally, by tracing hundreds of thousands of waves in the system and taking into account the Landau damping of the waves as they go from their source region into the inner magnetosphere, we are able to show in this paper that the waves from chorus can get access to the plasmasphere. And once they get access, they rattle around, they get trapped inside this density enhancement, and they turn from a discrete emission, they become mixed together and produce a Hiss emission. We've done further modeling of this to show that we can not only explain the access, we can explain the spatial structure, and the frequency structure of the emissions. And there was one thing that we weren't able to explain until more recently, and that is that you have to also account for some amplification in the outer plasmasphere, because without it, the amplitudes of the Hiss are too small, by about 20 dB. But if you take into account the amplification, which is done in a paper by Lin-Jin Chen, then you can get very good reproduction of the intensity of Hiss throughout the plasmasphere. We know that these Hiss emissions are actually highly structured. They respond very rapidly to the density structure. This is, we think, primarily due to a guiding process. When you have density gradients, this focuses the waves. And this is another paper by Lin-Jin Chen that shows how these waves, as they gain access to the plasmasphere, can be focused into these regions of higher density. Now finally, I want to talk a little bit about modeling of the loss from plasmaspheric Hiss. I think Dan might actually talk about this event more in his presentation. But as soon as we turned the radiation belt storm probe instruments on, we found there were not just 2 radiation belts, there were 3. There was an unusual ring of high energy relativistic particles above 2 MeV that was present at between 3 and 3.5 Re. And it slowly decayed, as you can see. And the decay rate was very energy dependent. It got much slower as you went to higher energies. So we took a model for the intensity of plasmaspheric Hiss seen both on Themis and the Van Allen probes, and used this to work out diffusion rates. And then in a GRL article published last year, we were able to simulate the scattering that occurs around 90 degrees, where most of the particles are injected, and get pretty good agreement with the slow decay that occurs as the Hiss works on these waves. The scattering timescales around 90 are on the order of 10 days. But interestingly, it would take almost a year to actually remove the particles and dump them into the atmosphere. So these are my conclusions. We think that chorus emissions are produced during the convective injection into the magnetosphere. They seem to be responsible for this global distribution of diffuse auroral emission. We can actually use this fact to actually get a global distribution of the waves by simply measuring the ratio between precipitated and trapped flux, and that was published also in a GRL article by Wen Li last year. We also think these chorus waves cause local acceleration and is the dominant process that initiates the acceleration of particles in the outer radiation belt. Subsequent to that, there's radio, and during that time, there's radial diffusion going on too, that can take particles inwards or outwards from the, the peaks in phase space density that develop. And then finally, the chorus is also important because it's the embryonic source that ultimately then produces the Hiss that is then finally the mechanism that finally gets rid of the electrons once they're injected into the inner magnetosphere. So I want to thank the radiation belt storm probe teams who provided much of the data I've shown in this talk. And I want to leave you with just a little video that was given to me by Alison Janes on the pulsating aurora, which we also think is due to what's happening here? There we go. So if you look here, every time you see pulsations, what you're really seeing are chorus emissions scattering the electrons out on the equatorial region on the same field line. And when we have this picture, it can be taken either from all-sky imaging pictures as shown here, or if we have satellite measurements like POSE, we can get a global picture of the distribution of chorus waves in the system. Thank you.
Questions, Bob?
One thing I'm a little concerned with is when you cite the work of Pat Newell on the relative contribution to the energy budget for discrete versus diffuse aurora. Pat has a very, very tight definition of what is discrete aurora. It's got to be a very narrow energy peak in the spectrum. So he's an extremely restrictive criterion for discrete aurora, and he may be mixing some discrete in his diffuse auroral statistics.
Well, he might. Agreed. But if you actually look at the distribution that he shows, if I can find it. Yeah. We know that the discrete aurora is primarily produced in this region westward of midnight, and that's where he sees his discrete. That's where he puts the discrete emission. Right. Whereas we also know that as the electrons are injected and drift around, producing the diffuse scattering, this predominantly extends around to the dawn side.
That's not what I'm disputing. It's a question of when you try and ask how much energy comes from discrete versus diffuse, there's a little bit of mixing, I think, in the diffuse statistics. There's some mixing of discrete. So
well, I'll let Pat answer that question to you, but I know he used tens of thousands of observations from DMSP to make this.
Richard, why does the re-energization with the chorus waves take place preferably near L of 3.5 or L of 4? Why is it that far into the inner magnetosphere?
Well, first of all, it's controlled by this ratio between the plasma and the gyro frequency, and that tends to minimize just outside the plasma pores. So that's why we think that that's the region where it works most efficiently.
So when you were talking about the chorus causing the diffuse aurora, is there a difference in the role of the upper band and lower band?
Yeah, there is. If you actually look at the diffusion, look at the diffusion rates, the upper band, because it's higher frequency, tends to resonate with electrons anywhere from a few hundred eV up to a few keV. The same energies that resonate with ECH waves. Whereas the lower band tends to resonate with electrons typically above 10 keV. So the higher energy particles are dumped by lower band, the lower energy particles are dumped by the upper band. Yeah. Well, they're different, yeah. But you see, the chorus can interact, as you can see, anywhere from a few hundred eV all the way up to MeV energies. So they will also scatter the 30 keV stuff, which is seen by POEs, the 100 keV stuff seen by POEs,